Okay, Federico, welcome.
Yeah, thank you very much. I'd like to start by thanking the organizing committee, particularly Claudia and Mina, for the invitation. The title of my talk for this workshop is Wave Interactions and Ionosphere-Thermosphere Variability. This presentation, I've divided this presentation in 4 different sections. In the introduction, I will provide an overview on forcing from below, and also on the current status for tidal and planetary research, as well as present an approach for establishing how tides and other waves are driving the lower thermosphere, ionosphere. And then I will present a very brief overview of the whole atmospheric climate community model with thermosphere, ionosphere, and extension, WACCM-X, and some of the key capabilities. Then I will describe wave interactions, how different waves can interact, and provide an example of some results taking advantage of some synchronous satellite measurements or solely processing satellite data that is effective at highlighting wave interactions. And then I'll present some conclusions. So here to start, this is a depiction from the National Academies of Sciences. It shows you in green the lower atmosphere, in gray the ionosphere and thermosphere. We have a region between 100 and 200 kilometers that we have been discussing, which is the lower thermosphere, ionosphere, or LTI region. This is a region highly forced from above with processes associated with the magnetosphere or geomagnetic processes, such as some that Gang discussed earlier, but also from processes associated with upper propagating waves. And usually atmospheric waves are characterized or categorized in 4 different classes. There are Kelvin waves, solar tides, planetary waves, and gravity waves. Hanley earlier discussed quite extensively gravity waves. Those are the ones that that are currently not very well. They're a large source of uncertainty and biases in the general circulation models in the upper atmosphere. But we also don't have a very good understanding on other waves, such as solar tides and Kelvin waves, for example. But what I'd like to point out here is that upward propagating waves represent the primary mechanism through which energy and momentum are transferred from the lower atmosphere to the LTI region. And among these, the large-scale solar tides and Kelvin waves really contribute significantly to essentially carrying that spatial temporal variability from the lower atmosphere and middle atmosphere to the LTI, and particularly at low latitudes and during for solar low and geomagnetically quiet conditions. So very briefly, it is well known how the low latitude LTI region is largely driven by solar tides, although research in the last, I would say, couple of decades has demonstrated the importance of lunar tides, Kelvin waves, normal modes, as well as secondary waves due to nonlinear interactions between solar tides, planetary waves, and Kelvin waves, and I'll describe those in further detail in the later part of my presentation. Solar tides are generated by lane heating due to deep tropical convection, as well as by solar radiation absorption, by water vapor, as well as nonlinear interactions that I'll describe, that essentially carry the longitudinal temporal variability from their source to the LTI. Now, the timed satellite has provided a very valuable measure for measurements for our community, essentially giving us an understanding of what the mean tidal spectrum entering the thermosphere at 110 kilometers looks like. And these measurements date back to 2000, so it has been over 20 years of very valuable measurements. Then we have also measurements from the CHAMP, GRACE, GOCE, and more recently Swarm, Gold, and Icon, and in a couple of years also all measurements that in the thermosphere in the 250 to 500 kilometer region have provided an understanding of what tides and other waves are capable of propagating to this region. And then we have used tidal theory for filling the gap to a certain degree, but we have lack of good measurements between 110 and 250 kilometers, which are really needed to understand a lot of the wave propagation characteristics. So we know what the main tidal components are, and we know also which ones are highly capable of propagating to the LTI region. For example, the diurnal eastward 3 tide, that is the main source of wave 4 longitudinal structure in the LTI region. Primarily, what we don't understand well is the short-term variability, defined as variability between days and weeks of solar tides. And this is due to the fact that we don't have a good global sampling in latitude and longitude from ground stations, as well as due to the fact that we have a slow local time precession period for single satellites. And we have been able to look at, for example, at D3 tides on a daily basis, but with significant assumptions. So an approach for establishing how tides and other waves drive LTI variability is the following. We want to measure all the relevant parameters such as tidal winds, temperatures, composition, and electric fields over as much of the domain as possible. Then we want to develop physics-based relationships between these different parameters and use them essentially to infer what the driver-response relationship is. Then we can employ a first principle model to enable a multi-physics interpretation. And finally, we can use the measured wave fields to drive the first principle models. And so then we can validate dissipation and propagation of the waves in the LTI. One of the physics-based models for our community is the whole atmosphere, going for a couple of decades at the High Altitude Observatory at NCAR. It is a model that goes from the surface to the thermosphere, and it includes the ionosphere. The WACCM-X is, as I'm showing here, based on the WACCM model, which is in turn based on the NCAR CAN model, which is the Climate Community Atmosphere model, which is a component of the Community Earth System model, or CSM, and it's coupled using a coupler. And what I'd like to point out is that it's an open source model that is publicly available and can be downloaded from the NCAR CSM webpage. The horizontal resolution for WACCM-X in the standard configuration is 1.9 degrees in latitude and 2.5 degrees in longitude, and a quarter of a scale high vertically, above approximately 1 hectopascal, and the time step in the standard configuration is 5 minutes. The 3-hourly output from an extended WACCM-X simulation on the version 2.1, the more recent version, dating back from the beginning of 2000 until the end of 2017, and soon until the end of 2019, in the specified dynamics configuration is available on the NCAR Climate Data Gateway, can be accessed at this DOI. And the data sample along the orbit of the CHAMP, GRACE, GOCE, and SWARM satellites is also provided and can be used for comparisons in studies for LTI science. As I mentioned before, a source of variability in the LTI region is due to the interaction between different waves. In particular, evidence has shown both observationally and modeling that planetary waves can modulate atmospheric tides, and their interaction is a large source of tidal and longitudinal variability in the upper atmosphere and ionosphere. In particular, the way that this interaction is believed to occur is through the generation of secondary waves that have different periods and zonal wave numbers than the primary waves that are originating them. So schematically, here I'm showing a depiction of a primary wave 1 and primary wave 2 defined by their frequency and zonal wave numbers. Essentially, as they can interact in a nonlinear forcing region, those are generating two secondary waves where their frequency and zonal wave numbers will be the sums and differences in the frequencies and zonal wave numbers of the primary waves. And so these secondary waves can propagate as independent waves and being affected differently by the background winds and dissipation. And so they're capable of propagating to regions where the primary waves would not be able to. And now to study secondary waves from satellite data is fairly hard because of the frequency that is very specific, and we don't have good temporal and longitudinal resolution. But a method has been developed to analyze those in synchronous and solid processing satellite measurements. And it was originally formulated by Mudden and Forbes several years ago, and it has been implemented successfully later. So here's an example of severe temperatures averaged around the equator for 3 years, 2010 to 2012. And in essentially, the time series is created where instead of time, we have longitudes. And if we then look at the periodicities in this longitude series, tides will occur at integers, and anything in between will be either due to longer period waves or the interaction between the tides and the longer period waves, such as planetary waves or Kelvin waves. And so in a pseudo-longitude, so-called spectrum, we see this peak here, for example, likely due to a 3-day ultra-fast gamma wave, as well as a strong wave 4 peak due primarily to the D3 tide. And then we also see the interactions, the K1 and K2 sidebands in the severe temperatures. If we then look at the GOCE densities for a concurrent period of time, and GOCE follow the quasi-synchronous orbit, we see evidence of the similar periodicities. The same approach has been also applied to MAVEN data, and the reason I'm showing this is because MAVEN followed an orbit that is somewhat similar to the one envisioned for the Daedalus mission. So if we're looking here at a period of time going from November 1st, 2014, we see altitude on this panel, the top left panel. The top right is solar local time, the bottom left is longitude, and bottom right is latitude. Essentially, what we have done was looking at measurements taken at periapsis between the altitude of 130 and 170 kilometers. We normalized those densities from the accelerometer on board MAVEN to 150 kilometers. And then we looked at low latitudes, plus or minus 15 degrees, that defined 4 different periods, of which only the third period we analyzed in further detail, and I'm showing results here for going for sols 613 to 652 in this particular period. And if we apply this pseudo-longitude spectrum to the MAVEN accelerometer, that's what's shown here on the top panel, whereas the bottom panel shows MCS, MRO MCS, temperatures also in Mars in the middle atmosphere at 80 kilometers. And what I'd like to point out here is that we are able to see the ultra-fast gamma wave peak at the 1.4 cycles, as well as the interaction with wave 1, wave 2, and wave 3 that is very well characterized in this pseudo-longitude spectrum. So pseudo-longitude spectral analysis is effective at identifying secondary waves due to nonlinear tide ultra-fast gamma wave interactions in the MAVEN accelerometer and MRO MCS measurements. And secondary waves are really playing an important role in coupling the lower and middle atmosphere of both Earth and Mars to the thermosphere and potentially the ionosphere as well for Earth. And so to conclude, planetary waves and comet waves can exert influence on the LTI through vertically propagating tides that are being modulated. And secondary waves are produced by the nonlinear interactions that are propagating as independent waves. Pseudolongitude spectral analysis can be used to identify and characterize nonlinear planetary wave tide and comet wave tide interactions from slowly processing and synchronous satellite measurements, such as those anticipated for the Daedalus mission. And the first principle models, such as the WACCM-X, may be employed to understand which waves are interacting and also to characterize their impact on the overall temperature, composition, and density structure of the LTI. And particularly, Daedalus perigee measurements near 150 kilometers in combination with physics-based models are likely to really improve greatly our understanding of the sources of LTI variability associated with nonlinear wave interactions. So we really look forward to a successful Daedalus mission. With that, I'd like to thank you and ready for any questions from the audience.
Thanks a lot, Federico. Very interesting, very nice talk, very clear. So are there questions from the audience? So one of your first slides, you mentioned that the local time precession of the satellite plays a role in identifying and analyzing waves. So what is sun-synchronous orbit or nearly sun-synchronous or slow processing orbit more suitable for wave analysis, or is a fast processing orbit, so with lower inclination, more suitable for wave investigations, planetary waves?
So I would say that it depends on the types of waves that you would want to be looking into. But ideally, you would want to have the most local times coverage. And I would say for some of the global scale waves, such as tides, if you're looking at, say, the D3 tide, then you would be primarily interested in the low latitudes where the D3 is particularly strong, primarily in the thermosphere. So you would want a faster processing satellite for that case. But if you're looking at a higher latitudes, you're then constrained by the
inclination.
So it's a compromise between how global you want to have your picture and how what type of averaging you're willing to accept for looking at the tides. And if you are interested in looking at the day-to-day variability of tides, then you might have to make assumptions such as taking an average between the data at the ascending and descending node, and in which case you are able to have some type of understanding of what the tide is, but then you don't have it's hard to differentiate between different tidal components as well. So
okay, thank you very much.